0 over 0? Yeah, not on my watch. Welcome back, future doctors and engineers. Are you guys ready for a completely new mathematical thrill? Today, we're totally ditching the dusty traditional lecture format. Instead, we are entering a high-stakes limits battleground. Why? Because today, we aren't just going to talk theory. We are going to crush the exact calculus problems that propel rockets into orbit and build the bridges we drive on every single day. So let's get into it. But first, let's talk about why this actually matters out there in the real world. At aerospace companies like SpaceX, calculating the terminal velocity of a descending rocket requires absolute pinpoint precision. If your limit calculation is off by even 0.001, that Falcon 9 rocket crashes and burns. It is literally that serious. So before we jump into today's mission, let's take a quick look at who mastered last week's challenge and landed safely on our Calculus Heroes leaderboard. A massive shout out to our top problem solvers. Your precision is exactly what the aerospace industry is hunting for right now. Okay, here is your mission map for today's boss rush. Number 1, we'll confront the 0-0 glitch. 2, the velocity siege. 3, algebraic rescue. 4, the factor trap. 5, proving precision, and 6, the final challenge. Let's go! Section 1, the 0 over 0 glitch, an indeterminate threat. So this is a moment pretty much every calculus student dreads. It's that exact moment when mathematical reality seemingly just glitches out, and the rules as we know them totally break down. I'm talking, of course, about the indeterminate form. You know the feeling. You plug in your numbers and you end up staring at a big, glaring 0 over 0. It feels like a total dead end. But here's the secret. 0 over 0 isn't actually an answer at all. It's a trap. Think of it like a flashing neon sign telling you that you simply cannot solve this by direct substitution. The true answer is hiding behind that glitch, and we just need to upgrade our mathematical toolkit to bypass the error and reveal the truth. Moving on to Section 2, Velocity Siege, the physical application. To really build that toolkit, let's take abstract limits and apply them directly to the physical world. Imagine dropping a ball straight down from the upper observation deck of the CN Tower. How fast is it going at an exact frozen snapshot in time? There is a massive conceptual leap here, guys. On the left, we've got average velocity. This one's easy. It's just distance over time, giving us the slope of a secant line between two distinct points. But on the right, we have instantaneous velocity. How in the world do you calculate speed at a frozen moment where literally 0 time has passed? You can't just divide by 0. So we use limits to capture the exact instantaneous speed, which is represented by the slope of the tangent line. Okay, let's run the exact calculation for time equals 2 seconds using our distance function, 40t minus 16t squared. Step 1, we set up our average velocity formula over a tiny time interval that we'll just call h. Step 2, we plug 2 plus h into our function, which, gives us some pretty messy algebra. Step 3, we expand that interval and simplify everything, which leaves us with a numerator of negative 24h minus 16h squared all over h. And here is the absolute magic in step 4. By shrinking that time interval h down to absolutely 0, taking the limit as h approaches 0, we perform this awesome microstep combo. The h cancels out completely, leaving us with exactly negative 24 feet per second. And notice that negative sign, that just means the object is falling back down to Earth. Section 3, Algebraic Rescue. Factoring the enemy. Now, what do we do when shrinking that interval plunges us straight into the 0 over 0 glitch right from the start? Let's look at the limit as x approaches negative 4 of the polynomial x squared plus 3x minus 4, all divided by x squared plus 5x plus 4. Step 1, direct substitution gives us 0 in the numerator and 0 in the denominator. Boom, the trap. So the crucial point here is that algebra is our absolute best weapon. Step 2, we factor the top into x plus 4 times x minus 1. We factor the bottom into x plus 4 times x plus 1. Step 3, do you see the cancellation opportunity? The troublemaker that x plus 4 is sitting right there in both. We slice it out, cancel it. By removing the glitch in the denominator, we safely bypass the trap. Step 4, plug in our negative 4 and we find the true destination. Negative 5 over negative 3, which simplifies perfectly to a beautiful, clean 3/5. Algebra literally saved the mission. Section 4, the factor trap. Time for some interactive suspense. Okay, you've cleared the basic glitch, and you're doing great, but don't let your guard down just yet. The calculus battleground is absolutely full of traps, just waiting to trip up unwary engineers. Pause this explainer for a second and really think about this critical scenario. What if, during your algebraic rescue, the denominator factored into a squared term, like x plus 4 squared? If you canceled one of them with a numerator, you'd still have an x plus 4 left over on the bottom. Could you still get a solid, finite number? Post your guess in the comments right now to lock in your answer. Got your answer? Well, the truth is that the limit does not exist. It just spirals off into an asymptote. This brilliantly illustrates that you must completely clear the factor trap and eliminate the division by zero entirely. If that denominator term doesn't completely cancel out, you are looking at an infinity, an asymptote, a totally different beast. You must entirely eliminate the glitch to find a solid point. Section 5. Proving precision. Welcome to the boss fight. You've survived the traps. Now we face the ultimate gold standard of calculus, the precise epsilon-delta definition of a limit. This is the heavy machinery used by top-tier mathematicians and engineers. Actually, forget abstract math for a second. Think of this like a manufacturing contract. In the real world, epsilon is your engineering error tolerance, like how much wobble or deviation can we realistically accept in the final product. Delta is the exact, strict precision you must deliver on the assembly line to guarantee that epsilon is met. You give me the acceptable error epsilon, and I will mathematically guarantee the required precision delta. Let's execute this precise mathematical sequence together. Say we are proving the limit of 4x minus 5 as x approaches 3 is exactly equal to 7. Step 1. We set the absolute value of our output error, 4x minus 5 minus 7, to be less than our tolerance, epsilon. Step 2. We simplify that algebraic inequality to the absolute value of 4x minus 12 is less than epsilon. Step 3. We factor out the 4, isolating our input factor, which gives us 4 times the absolute value of x minus 3 is less than epsilon. Divide both sides by 4, and we get the absolute value of x minus 3 is less than epsilon over 4. Step 4. Boss defeated. We choose delta to be exactly epsilon over 4. If your rocket needs an error tolerance of 0.1, I now know for sure I must keep my input precision tighter than 0.025. We have mathematically proved the limit. Finally, Section 6, the final limit challenge. All right, you've successfully navigated the velocity siege, you've factored out the traps, and you defeated the epsilon delta boss. But are you ready for the ultimate test of your newly upgraded skills? Here is your homework to get on the leaderboard. Can you solve a 1,000-degree limit? Imagine an indeterminate form where x goes to 1 and the numerator is x to the power of 1,000 minus 1 all over x minus 1. Direct substitution gives you 0 over 0. But how on earth do you factor a 1,000-degree polynomial? Here's a hint. Look for a pattern in factoring difference of squares and cubes and extrapolate that to defeat the ultimate indeterminate form. Can you crack this massive problem and get your name on the next leaderboard before our next explainer drops? Drop your answers below. Until next time, stay dynamic, keep calculating, and I'll see you in the next throw.